Welcome everybody to the Wheel of Fortune. We're going to be wheeling and dealing one more time with a tertiary. As you can see, when you draw a line from the alkyl halide to the carbon that it's attached to, there are 3 carbons attached to that point. So this is beyond any doubt a tertiary alkyl halide. Another feature about it is that it is chiral. Let's see what are the consequences for this molecule when you put it in different buckets containing or different test tubes containing different reagents. Let's look at it. First of all, we have to understand that tertiary is always the most sterically hindered. So you got a big R group here and an R group here and an R group here. It's going to whack anybody that's going to try to get near that carbon. Okay, so that's your electrophilic carbon. This is your leaving group. It's polarized, so you have a delta minus and a delta plus. And so nucleophiles are going to seek the delta plus. And iodine's just going to roll up those sigma electrons and leave as a octet, a stable anion. And so we have to see, well, what are the reactions with A, B, C, D class reagents? These are the good nucleophiles. These are the nucleophiles that are also very basic. These are bases that are typically not nucleophilic, just base. And here are neutral, weak base, weak nucleophilic solvents. What are they going to do for tertiary? Let's take a look. PPH3, dichloromethane. Well, this is huge, and this has got enormous amount of steric, can't get anywhere near there. This is in a polar aprotic. So polar aprotic promotes SN2. So you definitely would say no SN2. However, would there be anything else possible? Is there an E2 possible? No, it's not basic. About SN1E1. It's in an aprotic solvent, and those don't promote carbocations or cannot stabilize carbocations like a protic solvent like water or methanol and so on. Therefore, you wouldn't even have SN1E1. What about if you put this in an aqueous environment? Well, PPH3 is very insoluble in water. So therefore, that's not going to happen either. So we will leave it at that, no reaction. NaSH. Now I did take away the solvents that were here previously. Those were aprotic solvent. As I said, aprotic solvents promote SN2. These 3 groups here, you can see a huge branch, isopropyl, ethyl, and methyl. They're going to whack anybody who tries to get in the backside. Therefore, you cannot do an SN2. So I took off the aprotic because in aprotic, SN2 is the favored reaction. Otherwise, there's no point doing an aprotic solvent. Aprotic solvents typically also tend to be more expensive than, typically, not always, than the protic. So why waste your solvents here, putting aprotic, when there's really not going to be much of a reaction, and even if it is, it's going to be extremely slow mainly. So if you want to have a reaction with these, you would be very well off putting protic solvents. Protic solvents, for example, water, sodium NaHS, or methanol, let's say methanol or water. H2O, KCN is very soluble in water, NaCN, it's also soluble. I mean, these are all group 1 cation, ionic compounds are all soluble in water. So you could put water or methanol. Now you don't want to put water into KN3. This N3 minus, that's what you find in your airbag. As soon as you have an impact, it's going to explode. If you put water in there, you're going to explode right away. So you don't want to keep that out of protic solvent. So, and in aprotic, you're not going to be able to rattle that well enough to give you a backside attack. So let's go around this ring now that we have protic solvents and see what's going to happen. And it's the same with sodium iodide. If you want to have it, reacting in any kind of discernible timeline, then you'd want to have a protic solvent, and you know these are very soluble in water. All right, so if you have a protic environment, and I'm going to say protic, emphasize on that, then you would have SN1 major. Okay, so for all of these, for SN1 to happen, and I'm just going to do it one time here, you would have a ionization. So your protic solvent is going to come rattle this bond, and it's going to split into a carbocation and an iodide anion. So your carbocation is going to be flat, plus you have an iodide that's going to fall off with your sodium. Now NaSH can then come in and attack this both sides, up and down. Now we saw that when you had chiral compounds that were secondary, you would get inversion. For example, 1, 2, 3 R would give you an S inverted compound. But in this case, you're going to have the SH attack above and below. Or, I'm going to put or, it can attack from below the plane. Therefore, you can have two products, almost equal amounts, and where one of them is going to have your methyl down and the other one's going to have your methyl up, and your SH, when it attacks from above, will be above, and when it attacks from below, it will be below. So this is going to be a raceme, which means you have a 1-to-1. This is your intermediate, and that's your anion that's going to stabilize that. And it's going to fall off with your sodium and make sodium iodide. All right, so this is a general mechanism for all of these in protic solvents. In aprotic, you could say no reaction. If it's, and depends on the reagent, if it's soluble in protic or not. If it is soluble in this protic, and your reactant is soluble in this protic, then they could come together and give you SN1. So basically, you're going to rattle this and attack with your selenium up and down, and so you're going to get the same thing for both of these, for almost all of these reactions with protic solvent. So methyl selenide is going to attack from above and below on that intermediate. 1-to-1. Because you're forming a carbocation, it's going to be racemic. All right, let's look at KCN. KCN is going to have, again, potassium and cyanide dissociating. Potassium will be aquated. Cyanide would have aqueous, water around it. And so SN2 is going to be impossible. You have to wait for the water to ionize this. Now, another very important thing that we have to keep in mind in all of these reactions is that the solvent is also a weak nucleophile. So it can also compete for that carbocation. So these are, I'm just writing the major, but the minor could be where you would have the solvent, attacking, and that too can be a raceme. So I'm going to put a note here, major SN1, right? Minor solvolysis. That means you are going to have, for all of these, a small minor component where you would have the solvent, and it could be in all of these some oxygen something, OR or OH, or I'm going to put OH at the bottom if you use water, and that is also going to be a raceme. So that's going to be note, minor solvolysis for all of them. How much? That depends on the concentration and the temperature and so on, but basically concentration. The more of the reagent you have, the more you would have your major product. Let's look at hydrolysis here with KCN solution. So again, this is a very polar solvent, a dielectric constant about 79. So you can see this is going to really ionize this very well. It would be faster. And you would get your carbocation, and then your KCN is going to attack it from above and below. So that's your above and below, and this is going to be a 1-to-1. Your cyanide is going to attack from above and below. All right, let's look at this next one, water in sodium thiocyanide. Sodium thiocyanide, even though cyanide is deadly toxic, this one's actually okay. So you can take this, put a solution of this or a slurry of this, mix it all up, and you can do kinetics on that, and then you can have your carbocation being attacked by this above and below, SCN. And for all of them, minor solvolysis product. KN3, I'm just going to say no reaction because you don't want to put that in water. Okay, kaboom. Sodium bromide in water, is it going to do anything or is it just going to watch? Because we know iodide is a better leaving group than bromide. Bromide can actually replace the iodide, but can it do a backside kick? No way, bromide's also a huge atom, can never fit into that pocket there. You're going to have to ionize it with a very polar water molecule here, get a carbocation here, and then attack that above and below equally with the bromide. And then, of course, in all of this, the sodium iodide is going to form as a side product. So this is just a iodide is going to come off in all of this with the sodium. In this case, potassium, and you would have your sodium iodide. In this case, too, you would have sodium fall off with your iodide. It would be soluble in water though, and you could go back and forth on this reaction. I mean, you could go back and forth on most of them, but definitely this one. Because iodide's a good nucleophile as well. NaNO2, but is that basic enough to do an E2? It's probably not going to do much of an E2 there. It's going to do mostly SN1 in the presence of water. SN2 is not going to be possible again and again and again. I'm mentioning about the steric on tertiary. So it's going to be too slow. By the time it's ever going to get done, your SN1 would probably see the light of day during all of these reactions. And then, of course, your sodium iodide is going to fall off. Sodium acetate. Now, sodium acetate pKa is about 4.8. So it can be a little bit more basic. Is it going to do an E2 or is it going to do an SN2? Or an SN1? Well, sodium acetate again would like to do an SN2, but there's too much steric. It's a weak nucleophile. It's also a weak base, and it could do an E2. But here we have a protic solvent, which means you're probably going to have a lot of ionization there, and you will have SN1. In all cases, whenever you have basic reagents, you can also have E2 in addition to E1. So then you would get, in addition to this, E1. When you get E1, E1 always gives you the Zaitsev product. So this is the most substituted double bond. So it's going to form right here, E1. Bromide, for example, is not going to do an E1. these are not very, basic to do E1. However, cyanide could do E1. So over here too, you could get a little bit of E1. So you could have E1 here. Energy ethyl. So this is kind of basic. It's a good nucleophile, but it's also basic. And that itself would be a liquid, so that would be your solvent. Over here, this is going to promote more E2 because it's basic. So in this case, since you don't have any opportunities for backside attack, it's going to be major E2. So your nitrogen lone pair is going to grab a hydrogen here. This is your beta hydrogen. You have hydrogens here too that are beta, and you have hydrogens here as well. But since you have a nice space, it's going to go for the one that would have the most stable double bond, which means it's going to go for the Zaitsev product because the activation energy for that would be lower. So you would pull this off, kick off your iodide, and you will get a alkene that is more substituted. In this case, there's really no cis and trans because these are identical. What about this guy, a satellite? A satellite is very basic, right? pKa, in this case it'll be 25. It's very basic. There's no backside attack. It's going to do almost exclusively E2. It's a small base, therefore it'll prefer to do the Zaitsev. If you can do a Zaitsev, it will do a Zaitsev. But in cases where the base is extremely bulky, that's when you do the higher energy Hoffman. But Zaitsev is lower energy, lower activation energy to achieve. So molecules or bases that are small would always prefer to do Zaitsev or form the more substituted alkene. Here's an oxygen anion, oxygen 16 pKa, pKa 11 and above, you're going to get almost always E2 on a tertiary. So this is going to, again, small base, pull this hydrogen off, do a nice E2 over here, same deal as before. These are all your major products. No SN2. Now you may think, okay, we have some protic solvents here. Is it going to do SN1? Typically when you have a strong base, the base doing an E2 is faster than the multi-step SN1 or even E1. So you would mainly do E2. Even in protic. Same here, E2, major. Small base pulls off the hydrogen from the most substituted carbon, and those electrons run in, kick off the iodide to give you the most substituted alkene. All right, they all seem to be the same. I could very well have put all of these being the same deal here. Small base is going to give you an E2. Great. Now, what about when you have bases like this? These are bulky bases. They won't be able to access this hydrogen. It's kind of heavily guarded by these two methyl groups here. Can't pull that off. But it can go in here. Well, there is a methyl here too. But look at this. There's no side chains here. It's the easiest one to access. So it's going to grab that, pull that off, and kick off your iodide. So let me write that down. So it's going to give you an alkene between the CH3 carbon and the carbon here that has the iodide. So here's your iodine here. That's going to leave. And then you would have an isopropyl and a ethyl. So your base is going to be, let's say, your T-butoxide. That's going to pick that up. That's going to drop those electrons on that bond here and bye-bye iodide. So you're going to have a double bond right here. So that's going to give you a double bond right here. This carbon is going to just have two hydrogens, and this carbon is going to have a isopropyl and ethyl. And again, there's no cis and trans because these two are hydrogens. And then you'll have, whatever your potassium or iodide, whatever coming off, falling off. It's the same with DBU and DBN. These are enormous bases. There's no access here. So it's going to go mainly here. This is going to be your major. Now, with the t-butoxide, you could have a minor over here. You could. So I would say for over here, you could have a minor between these two. What about sodium hydride? Is it also going to go for the less substituted hydrogens? No, not really. It's really small, so it can access that. But it's not going to do any SN2. Well, it's almost impossible here. It's going to give you the same thing as here. Great. We're going to come to this section where you only have the protic solvent. They're weak base, weak nucleophile. Can they do anything to this really crowded alkyl halide? Well, yes, they can. We said over here that it's these solvents that are going to rattle that bond. And here you're going to rattle it. There's no really any other nucleophile except the solvent. So the solvent's going to then attack the carbocation. Would there be a rearrangement? Well, you're already on a tertiary. And so you really don't have to worry too much about rearrangements. Now, if you really heat this up, you're going to have more and more E1. So with the water, you're first going to form your carbocation. And your carbocation is going to have a positive charge right here where you had your iodide leave. You have a p orbital here. And the p orbital is going to be symmetric, going up and down, and that's going to be attacked both sides with the water. Now again, we can see that this is going to be hydrolyzed by water. So if you have, well, this is first going to be stabilized. You'll have these ion dipole interactions with water, and you'll have about 6 of these. Most cations have about 6 of these. I'm only going to draw 3 here, and then one of them can just slip in. Oh, seems like a really nice vacancy here, empty orbital and all. No one's watching. I'm going to just slip in here. That's the most common thing. So you can do an SN1. You're substituting with a nucleophile, but this is a slow step, so it's unimolecular. So that's going to give you a water molecule, the nucleophile above and below. Well, it's going to get, again, deprotonated by another water molecule. And I'm going to cheat here since I don't have space. And you're going to get a hydroxyl. So after deprotonation here, you will get a hydroxyl. And that would be your major. Sometimes it would be like 4/5 of the product. A little teeny bit of E1. You can see that this water can also access this hydrogen. Let's say you have a hydrogen here. It's really close, but I can grab that and push those electrons onto there. So that's the other thing that could happen. If I were to draw an arrow, I would say, okay, go over here and push those down. So 2 things can happen. Either you can directly attack the nucleophile, or you can pull off the beta hydrogen. So E1 is going to give you a double bond. Always sides F product for E1. That's one thing that you don't really have to mull over and break your head over. Is it going to be Zaitsev, Hoffman, which direction? It's always going to be the most stable, lowest activation energy alkene, which is the Zaitsev product. And here you can see it's tetrasubstituted, so why not? There's no cis and trans, so we don't have to draw a Newman projection. All right, so methanol, again, going to rattle that, give you a carbocation like this. You'll have your methanol with a CH3 here, so you'll deprotonate this hydrogen and end up with an OCH3 instead of a hydrogen. Again, the carbocation can be attacked above and below, so you would get both R S in equal amounts. S and R. And that would be your major. Minor would be an E1. That's your minor, and it's always going to be Zaitsev. Well, almost down to the last spin here. We got HBr water. What's going to happen with a hydrobromic acid? Those are very strong acids, which means you're just going to rattle that bond and completely ionize it. And then you're going to hammer it with whatever is in excess is going to hammer it more. So bromide would hammer it if you had a concentrated solution. Water would hammer it more if you had a dilute solution. But you would get a mixture of hydroxyl, which is an alcohol, and bromide. And they would also go through a carbocation intermediate, just like here. And you'd have your nucleophile attack above and below. And so you would get a up. Well, there's going to be a lot of products here. And since you have water, if you heat it up, you can also get minor E1. But major is what we're focusing on now. And I'm going to draw all these templates here so we can put our bromides and our water here. Plus minor, very minor E1. I would say very minor E1. Maybe a few percent of your product. So your bromide is going to attack below or above on that carbocation. Water is also going to be competing for the same spot, and it's going to attack above and below, get deprotonated. And a very minor E1, and all the minor E1 products are the same. That's it. All right, last one on our protic solvent. What is that going to do? Well, that is actually a protic amine. Amines are basic, and there's no chance of doing an SN2. It's going to do only E2. What about SN1 and E1 in a protic solvent? Because the nucleophilicity is so good and the basicity is high, SN2, E2 always are a little faster than SN1, E1. So by the time your E2 and your SN2 get done, there'll be very little substrate to do SN1, E1. Also, the basicity here is really the most prominent feature of this diethylamine. So therefore, it's going to do a very nice E2. So it's going to do an E2, and it's not too bulky, so you can do a nice E2 with a Zaitsev. If you had one, let's say you had one more ethyl, or you had LDA, lithium diisopropylamine, now that is a huge base. That's not going to do a Zaitsev. That would do a Hoffman. Okay, so just to complete that, if you had LDA, that is lithium diisopropylamine, and you're going to see LDA quite a bit later on, so I'm just going to introduce that as LDA. If you had a big bulky base like that, that is going to do entirely E2, and it's going to do E2 with the less substituted hydrogen. So you would get pretty much the same as a T-butoxide product there. Just a little summary, everybody. We have a tertiary alkyl halide. The tertiary alkyl halide is also chiral. What are the things that could happen to a molecule when you throw in reagents like good nucleophiles that are basic, just plain bases, and protic solvents, weak nucleophile, weak base? If you have a class which is a good nucleophile, it really cannot do any backside attack, so there's really no SN2. However, if you want to replace this iodide with the nucleophile, then you could use protic conditions. We saw earlier that when you have a tertiary and you have a protic solvent, it's a lot faster than when you have a tertiary and an aprotic solvent for nucleophilic attack. Therefore, if you can dissolve them in protic solvents, and you can get a good concentrated solution, and if you add to this, then they can ionize this iodide just like here. So this is your rate determining slow step in an SN1, and give you an intermediate carbocation. The carbocation would be flat, which means you can attack from below and above, and so you can get 2 enantiomers. And it's a 1-to-1 mix just because it's flat and there's equal opportunity above and below. So it's a raceme. These are not considered bases. This could be slightly basic. Therefore, you could get E1. When you don't have basic anions and you have just purely good nucleophiles that are good, then you would only get in a protic solvent SN1. Now, if you have slightly basic anions like this, you could also get E1. Now, in all of this, the solvent is protic, so the solvent could also attack this, and you could have solvolysis. And, depending on the concentration, you can get different amounts. And whenever you have SN1, remember you always have a minor E1. So that is a possibility. So protic solvents can cause a minor amount of E1 in addition to the SN1. Let's look at these, but you have, bases here, and all of these are small bases. Even though this is a good nucleophile, it's actually very basic. pKa is about 25 for that acid. So therefore, you are going to have a lot of E2. And the E2 here is going to form in such a way that you would have the most substituted alkene forming during the transition state, because that's the most stable, because the iodide is going to leave and it's going to give you an electron deficient transition state. So friends who can donate are really going to help out. So that's the preferred alkene, is the Zaitsev alkene. And you can see almost, if you have a small base, they will always give you an E2 Zaitsev product. Now, if the base is really very bulky, can't really get in here, it can only get in here or here. This is actually less sterically hindered because it's not branched. Then that's what it's going to do. It's a kinetic base. This is a thermodynamic base to increase the more stable product. So these are going to pull off these hydrogens and give you a di-substituted or a less substituted alkene, which is the Hoffman product. When you have protic solvents here, they are not strong enough to do an E2 or an SN2. However, they can ionize this bond. Their dielectric constant is high and give you a carbocation. The protic solvent can attack that and give you up and down attack and give you a raceme, SN1 major. It could also pull off a hydrogen on the most substituted carbon and give you a Zaitsev alkene. So E1 is always going to give you Zaitsev alkene. And these are very similar situations. If you have a base that's protic, and this base especially would give you major E2. So let's look at some more examples, and we will see you soon. Talk to you soon, guys. Bye.